So I'm Peter Davidson, University of Cambridge.
I'm Emmanuel Dormy, senior researcher in Paris at the ENS.
I'm Ulrich Christensen from the Max Planck Institute for Solar System Research in Germany.
I'm Matthew Browning from the University of Exeter here in England.
And I'm Chris Jones from the University of Leeds here in England.
Well, we work on dynamos that generate the magnetic field of the Earth, of other planets, of stars. And this is a fundamental physical question. And about 100 years ago, it has been suggested that these fields are generated by a dynamo process. Of course, we all know technical dynamos, but they work only because it's a complex arrangement of wires and sliding contacts and so on. Whereas, for example, the Earth's iron core is an unstructured big ball of fluid, and it's much more difficult to understand how in such a system a magnetic field can be generated. And so that's
another aspect maybe that makes this problem interesting and difficult is the fact that because it's so hot in the interior of planets and stars, there cannot be any permanent magnetism. So the field has to be generated through a self-exciting dynamo, not through motion with a magnet, as would be the case, for example, in the dynamo of a bicycle, the old standard dynamo we had on bicycles a few years ago.
I guess one of the things that's really unique about this problem and interesting about it is that it really does unite all these different pieces of physics and mathematics. And there are people here studying, some of us work on planets, some of us work on stars. I come from the stellar community. We live next to a star with some magnetism, and yet the underlying physics of that problem is really the same.
Well, one reason why it's timely is that in the past years or decades, we found out a lot about details of the magnetic fields, for example, of other planets than the Earth, like Jupiter, or the biggest moon of Jupiter, Ganymede, has a magnetic field, but also about magnetic fields of stars, which are much more further away, much more difficult to map, but it's still possible to determine what's the strength of the magnetic field and also what's their structure and topology. And we all want to understand what makes these differences in the magnetic fields that we observe.
Magnetic fields come from deep inside the planets, deep inside the Earth, and deep inside planet Jupiter, so that by studying these magnetic fields, we can hope to learn a bit more about what's actually going on inside the giant planets and inside the Earth, in a way that is very difficult otherwise when you can only just look at the surface.
And maybe one of the remarking properties of these dynamos is how this instability generation of the field can happen at such a wide variety of scale when you think of a planet as being a large object to the human scale. But a star, of course, is much bigger, 100 times bigger for the sun, and then the same instability also occurs on the scale of galaxies, and then the planet will really be a microscopic object compared to that. So it's a problem that applies to a wide range of scales across the universe.
Well, one reason for that is that today there has been a big problem theoretically to explain how a dynamo can work in stars or planets. And in the last 1 or 2 decades, we saw tremendous progress in big, large-scale numerical simulations of this process. And for example, for the Earth's magnetic field, we are now in a situation that within such simulations, we can explain actually many properties of the Earth's magnetic field, not only just that it looks like a bar magnet at first glance, but also how it changes with time, what is the fine scale of it, and why does it occasionally reverse its direction. And we are not quite as advanced, probably, I hope it's fair to say, with understanding stellar magnetism, but certainly we can expect more progress also in this direction. And so it's a rapidly developing field, aided strongly by direct numerical simulations, but also by the new observations, and hopefully by interacting between astrophysicists that either model the field or bring on new observations, and geophysicists who better understand the Earth's magnetic field. We hope we can make a lot of progress by this kind of mutual interaction.
Yeah, I mean, on the stellar side, the big thing that makes this timely and interesting to us right now is just the flood of data. So we're getting an enormous amount of data about magnetism in stars other than the sun. Just to provide a little context, the sun is magnetic. It has one example of that are these dark blemishes that appear at the surface of the sun, sunspots. Those are happening because a magnetic field has essentially popped out of the surface of the sun and is inhibiting the convective heat transport a little bit. And the overall sense of the sun's magnetic field flips every 11 years. We still don't have a detailed, sort of theoretical understanding of why that occurs on that time scale and not why it's not 20 years or 100 years or 5 or whatever. And one of the sun's this amazing laboratory for this kind of stuff, for studying dynamos, but it's a laboratory you can't twiddle, you can't control the knobs on, right? So we can't spin the sun up faster, we can't change its luminosity. By looking at other stars, we can effectively do that. We can look at stars that rotate a little bit more rapidly than the sun, or that are a little brighter or a little dimmer, and it's really only in the last decade or so that we started to get enormous, there's been data for longer than that, but there's really been a flood of data in the last decade or so that is providing us really powerful constraints on the kinds of magnetic fields you build in stars other than the sun. And that tells us something about how the sun builds its field too.
We're also learning a lot more about the fields of the giant planets, Jupiter and Saturn, particularly Jupiter. The Juno mission is currently going around Jupiter and is providing us with a fantastic degree of accuracy for measuring the magnetic field. Before, we only had a very vague idea of what Jupiter's magnetic field was like, viewed from a very long way off. Now we've got a mission that's going around right close to the surface of Jupiter, and it's producing hugely more data than we ever had before. And this is really changing our views about how Jupiter's magnetic field may be generated and what is going on deep inside the planet.
And maybe one thing we should stress is that besides the progress in numerics and in observations, which are very timely and very impressive, there's still the need for mathematical development, which is one of the reasons why the program is taking place at the INI, because it's not enough to just have measurements, observations, or have numerical models which produce colorful figures. One needs to have a theoretical understanding of what's happening, and this relies on technical mathematical developments with very small parameters, expansions, and so there's a lot of work going on which is at the interplay between all these aspects of the problem.
I think that's one of the really exciting things about it right now. It's just that we're starting to make contact between these different things, right? That is, as Emmanuel said, many of these theories, theoretical models of how this stuff comes about, are sort of in an asymptotic regime where some parameter is asymptotically very small or big or whatever. And it's only really in the last few years that I think numerical simulations are starting to approach that regime too. So you're starting to see this overlap between what the simulations can do and what the theoretical models in some asymptotic regime suggest they should do, and then on the other hand, what the data is going to be telling us. So that's really exciting.
Well, one of the challenges is, personally, I'm a numerical modeler, so I do simulations for the Earth's magnetic field or other planetary magnetic fields. However, in terms of some essential parameters, for practical reasons, we are many orders of magnitude off of the actual parameters in, say, the Earth's core. And so we get solutions that in some respects look like the Earth's magnetic field. For example, then can explain the detailed structure of the present day's Earth's magnetic field, but typically these simulations, they don't show reversals of the magnetic field, which are a well-known fact. The Earth's magnetic field reverses a couple of times in 100 million years. We have other simulations that don't look so nice or not so similar like the present magnetic field, but they do show these reversals. So there's really a gap still, and clearly it has to do with that something is still not captured in these numerical simulations, and that's the point we want to make progress on and understand. How could we change or adapt these models that we get the whole thing?
Perhaps a related point is that, as far as we can tell, motion in the core of the Earth and the other planets is incredibly complicated, extremely chaotic, very three-dimensional, lots of things happening, in many cases driven by different sources. But when you look at the magnetic fields of Saturn, Jupiter, the Earth, from a distance, all you see is a steady bar magnet, more or less, occasionally reversing. So a great interest is how this very, very complicated, messy, chaotic, three-dimensional flow in the core of a planet can create something so steady and so simple and so ubiquitous. But I think considerable progress is being made in that direction.
Yeah, it's a similar story in stars, I guess. I mean, if you look at the sun, the smallest scales that might plausibly matter in the dynamo process in the sun are maybe smaller than this room, right? And then the largest scales are the depths of the convection zone. So it's a factor of maybe 1 million or so dynamical range in each of 3 spatial dimensions. You can't, directly compute all those scales in a computer model, and you won't be able to for my lifetime, certainly. And so it's really at that blend between what you can do with numerics and the regime that you'd really like to be in, which is way the heck off. So that's the challenge of the thing, is really trying to extrapolate from what we can do to the regime that we'd like to be in. And as Peter said, I mean, observationally, we see that amidst this incredibly chaotic, in a star like the sun, the surface is there's this turbulence, it's very chaotic, and yet there's still somehow order. So there's small-scale magnetic chaff that constantly comes and goes, but there's also this much more ordered field that emerges as sunspots, a global dipole, and it has these very regular patterns of propagation and evolution that we still don't really understand. So to me, that's the big challenge. How does that order emerge out of this incredibly chaotic system with lots and lots of link scales?
Maybe to complete the approach on numeric, which will be as is introduced for the Earth, there is this question that the parameters of the Earth are very difficult to achieve numerically, so it's very challenging, uses huge computers in order to push the models to their current limits and try to approach the regime, but there's also the mathematical question, which is of interest, of whether the limit system, when you drop all the small terms in the equation, has a solution. And this, amazingly enough, is still an open question from a mathematical point of view. We don't know whether the limit system, which in our problem is called the Taylor state, has a solution. So this is also one of the points that is being discussed in this program. None.
No, he's a bit extreme. I mean, for most of us, the main interest is because it's a very fundamental theoretical problem that is partly understood, but many aspects are only poorly understood, and that drives most of us. However, magnetic fields do play a role also for society and for mankind, and one shouldn't exaggerate, but for example, the Earth's magnetic field shields us to a certain extent from cosmic rays that otherwise would hit the atmosphere, and or which could be a threat, for example, for low-flying satellites whose electronics is very sensitive. And so if there's, for example, solar flares, which are bursts of particles emanating from the sun, and if they hit the Earth, well, down here not much will happen, but it could be a threat actually to low-flying satellites. And so understanding better what causes, for example, these solar flares, and maybe someday even be able to predicting them, could be of help, really, and could save dollars or pounds or euros.
So if I can bounce on that, so my point of view is that the Earth field is important. It's true, it has applications, but what we're doing is not application-oriented. We're really trying to understand why there is a field, how it's generated, just because it's unbelievable that humans are living on Earth and not understand why the compass needle is pointing to the north. So it's something which is just an academic question which we try to address. It's true that having a field has an effect, but understanding dynamo theory will not change the field in itself. So we're not acting to try and protect humanity, mankind from solar wind or anything like this. We're really trying to understand an academic question which is important, and it's impossible to accept that we are living on this planet without asking these questions.
Yeah. It is true, though, to say that slight disagreement with the matter, but magnetic fields do play a very important role, actually, in our planet, because they really generate the space weather. The space weather that's coming all around us is actually coming essentially from the sun and from the sun's magnetic field. And so understanding how that magnetic field is generated will, I think, at some time in the future enable us to predict what's actually happening about space weather. And if you start looking at extrasolar planets, life on other planets, then what is actually happening in the magnetic fields of the stars as these planets are going around is actually very important for whether there is likely to be life on those planets or whether they're going to be habitable. So there are issues that will come into focus once we've eventually understood how these magnetic fields are being generated. But it is, of course, that's a long-term objective.
As I said, I mean, we do live next to a magnetically active star, and so understanding just where the field comes from, why it does the things it does, and that has real impact, not just on stuff like satellites, but I mean, that interaction between the solar wind and Earth's magnetic field is what gives us the northern lights, and things like that. So just at a deep intellectual level, we'd like to understand where that comes from. As Chris said, I mean, there's also an enormous amount of interest on the astronomical side right now. Partly it's just a kind of prosaic thing that if you want to go and detect planets around other stars, Earth-like planets, let's say, because we'd like to find an Earth twin around a Sun-like star. One of the big barriers to detecting and characterizing those planets, just observationally, is that stars are active. Other stars are magnetically active at a level that can sort of drown out a lot of the signal that you're looking for. So and in fact, that's where a lot of the interest on the astronomical side is coming, and a lot of the data is coming from really planet-finding missions, which are also great characterizers of stars. So as we're getting that data, people are trying to sort out what signature, how do you separate the magnetic signature from the signature of planets, or things like that. And as Chris said, also the habitability of planets that are close in. So for example, about 70% of the stars in our galaxy are these dim, low-mass stars called M dwarfs. Those tend to be quite active magnetically, and the planets that are sort of habitable planets, meaning in the area where liquid water could exist at their surface, they'll be very close in to those stars because they're dim and cool. And so you might expect that they'll be rather more affected by magnetic activity from that host star than we are. So there's interest on the astronomical side as well. But as Emmanuel said, I mean, we're really doing it to just as an intellectual and physical problem, which we hope some ways down the road might have some impact on other stuff.
Oh, definitely, there could be novel collaborations. Because I think in our program we have participants with a very broad diversity of background, starting with more people who look at the fundamental mathematical questions. There are the numerical modelers. There are people who do observations of either the Earth's magnetic field, how it is today or how it was in the past, the magnetic field of the sun, of the stars. So it's a very broad spectrum, and they're quite interesting discussions. I mean, we talk to each other, usually occasionally, but this is an excellent opportunity really to have lots of time for detailed discussions across different fields and understanding, on the one hand, what are the limitations of people who do observations, but also what are the limitations of people who do the models.
Yeah, for once, I'm sorry to say we do agree. It's true that the INI is an amazing place where people gather and meet very informally. It's meant for people to discuss, and so people with very different backgrounds, such as paleomagneticians, dynamo theorists, mathematicians, they all have coffee together and discuss, and it's quite clear, we can see that already, that new collaborations are emerging from that.
And you can see that just looking at these organisers. So Chris is an applied mathematician, Matt's an astrophysicist, Lee's a geophysicist, Emmanuel, I think, is currently a mathematician. I'm an engineer studying fluid mechanics, and I think this is really very unusual for an INI program to just pull people in very naturally from very different disciplines, and they talk and they swap ideas, they have different strengths and backgrounds, and it works very, very well, I think.
Agreed.
One of the fun things about this problem is that, I mean, the physics doesn't know which object you're looking at, right? And yet academic departments and things tend to be a little bit more siloed. So I think it's definitely the case that there's a lot of commonality between these problems, but I'm meeting all sorts of people from the planetary community that I haven't really interacted much with, and learning about interesting problems that tell you about the same physics that so I've studied in the context of stars, but in a different light on the same problem, really.
Done.